luminosity-distance relationship without electromagnetic counterparts, but that's a bit specific, and I've ended up putting lots of stuff all around the topic of using gravitational waves for cosmological inference. So cosmology in general with gravitational waves. So this is the same slide I had up with a different picture for the other talk. It's a discussion session. I'm going to try my best not to just talk for an hour and a half. I want to give a brief introduction to the topic. I know there are probably some people here that aren't too up to date with how we would go about doing cosmological inference using gravitational waves. And then at the end, I've got a random brain dump of questions and open things that I want answers for doing this. And again, please interrupt me as I go on if there is something that is not clear, because in fact, I really do need help. If you have any ideas about how to do some of these measurements better, or how to do any of these measurements at all, I would really like to know. Okay, let's get started. Some basic, it's all very, very basic cosmology. So if you thought this was going to be an in-depth discussion of cosmology, you're mistaken. So basic cosmology, the general idea. So just some non-gravitational wave things to start with. So one of the best ways of doing cosmological inference and working out how our universe is to look at the cosmic microwave background. It's an incredibly powerful tool to tell us some things about the universe. This is your classic map of the cosmic microwave background sky taken from Planck, looking at the temperature variations over the whole sky. This is obviously had the mean removed and false color applied, but these are variations of the order 10 to the minus 5 in the background temperature. What you can do with this map is you can take angular spectra and look at the power, the correlation between on various angular scales on the sky, and make this spectrum. And the blue points are the data, and the red line is the model that is fit to it using a thing called lambda CDM, lambda cold dark matter, the sort of standard cosmological model that we have. I won't be talking about different cosmological models because, as I'll say in a minute, gravitational waves is in the very early days, and we won't really be probing those different aspects of between different models. To start with, we'll be estimating parameters of those known models. So this is an incredibly good fit to the data. And you get some incredibly good numbers, including the Hubble constant and a whole bunch of other numbers. And the Hubble constant is particularly interesting for gravitational waves because that's one of the only things initially that we're going to be able to measure. So I'm going to focus, I talk a lot about Hubble constant. At the very end, I'm going to ask you whether I should even bother talking about the Hubble constant. The other sort of standard way of measuring things like the Hubble constant and doing cosmological inference is using standard candles. And the best one is a type 1a supernovae. So these are supernovae that go through, they're thought to be white dwarf stars that are accreting material, and at a certain point in their accretion, they surpass a limit, and they have a supernova explosion. And so you would think that all type 1a supernova, to within a few little slight discrepancies, would all explode at the same mass and be made of the same stuff and have the same luminosity in their explosion. And that's the most important thing. They'd all they'd all have the same intrinsic luminosity. And I'll talk a little bit about that more in a minute. But what you can do is you can plot this thing called distance modulus, which is related to the distance, against the redshift that you see for these events. Plot a curve through it. And this curve is a function of your cosmological parameters that you don't know, and you find your best set of cosmological parameters, and that gives you your cosmology that you've inferred from these things. So this is a distance versus redshift relationship, and I'll talk about that in a little bit. One other thing I wanted to point out is that in order to do this, because you don't know the intrinsic luminosity of a white dwarf supernova, type 1a supernovae, all you know is that they're all the same. What you really need is to find one where you know exactly how far away it was, and therefore when you measure the brightness, you can work out how intrinsically bright it really was and use that as the standard and compare that against the rest of things. And you have this thing called the cosmological distance ladder that is part of doing this. Well, oh, sorry, I didn't say this very clearly. So they're all, my understanding is that they're all white dwarfs in a binary system accreting matter from another object. And at some point, they've accreted just too much matter to go past the Chandrasekhar limit. And they want to form a neutron star very quickly and have an explosion, a supernova explosion. And they've just passed this threshold, and this threshold should be universal. So all white dwarfs doing this should explode at the same mass and have therefore this, and they're all very similar, they're all the same objects, so they should all have the same explosion, the same intrinsic brightness. Is that clear enough? I haven't thought about that for a while, so it wasn't a particularly clear explanation. Yes, yeah. There's a whole host of, so my argument with this is the whole host of physics into putting the points on this plot. And when there is a whole host of physics involved, there's a whole host of errors. So it's a lot of complicated, excellent science that they do to do this, but there is the potential that there are systematic errors in here. All right. So here's my plot, sort of trying to show that. This is from a recent, that's come out weird, recent paper comparing all of the recent measurements of, this is focusing on one parameter that is a function of these models, the Hubble constant, and you'll see in blue and red there are two distinct different types of measurements. In the blue, this is measurements made from these standard candle type observations using the distance ladder to calibrate it, and I haven't gone into the distance ladder, but there's a whole host of physics and measurements that go into calibrating these, and you can see the errors are getting better, and they're honing into a value of the Hubble constant around 72, is that 70? No, 73 plus or minus a few. Then on the other hand, you've got these the lambda CDM sort of approach from the cosmic microwave background, looking at different WMAP, different experiments, different analyses of the data, going up to the Planck measurements, and then this baryon acoustic oscillation measurement based on the Planck measurements, and they're all converging at a slightly different value. So there's some tension at the moment in this one important parameter, the Hubble constant, very simple parameter, just relating the recession velocity of galaxies and their distance from us. And what I put here is gravitational waves. Could a gravitational wave measurement of sufficient accuracy help resolve this current tension? That's right. They're looking at completely different scales. Yeah. And the lambda CDM cosmic microwave background is looking at redshifts, or the data's coming from redshifts around 90. I think it's 90 or so. The time of, is it reionization? Oh, is it more than 1,000? Sorry, I'm thinking 900. I'm thinking okay, I read 900 somewhere. And yeah, okay. Not sure. Okay. Right. Right. Okay. I think so. But that's calibrated against the Cepheid variables, so it's all related to this other physics, other observations. So in the near term, there is this motivation that we could possibly help resolve this issue before they resolve it, or we could agree with one of these, fill this gap in between. That's what I wanted to just put out there to start with. So, onto basic gravitational wave cosmology or cosmography. So I always have used these sort of interchangeably, and I had to look up what they really are. Cosmology and cosmography, technical definitions. Cosmology is learning about the universe. Cosmography is mapping the universe. But it's kind of the same thing here. So it's very akin to the standard candle approach, and again, the slides are not in the best order perhaps, but we call these things standard sirens. I'll talk about that in a second. But the idea is that we want to place points on the redshift luminosity distance plane. If you can measure the redshift of an object and its distance, and you get this via gravitational waves or any other way, you can put it on here. The line that the function that that relates the redshift and luminosity is a function of these cosmological parameters. And so here's just a few different curves for different cosmologies. If you then make some measurements, here's a bunch of measurements with error bars on them, and let's say I've made them from gravitational waves, gravitational wave observations, then you will fit a curve. You will do something a little bit more advanced to do with the Bayesian techniques we've talked about throughout the last couple of days, last week, and you will get an estimate for these parameters. So that's the general idea in the near term for how we would do gravitational wave cosmology, and there are variants of that, and I'm going to go and talk about the different variants from this point on, I think. And there's a definition of redshift related to the recession velocities of galaxies. Here we go. So I mentioned standard candles, these type 1a supernovae and other types of supernovae that can be used as standard candles. And we have the analogy with gravitational waves, specifically compact binary coalescence, binary black holes or binary neutron stars, inspiraling around each other and merging, just like the detections that we've had, or at least the black holes that we've detected. With standard candles, the idea is that you somehow calibrate one candle, you know exactly how bright it is, and then you see another candle. If I see another candle 4 times less bright, then by the inverse square law, I know that it must be twice as far away. If I see something 16 times less bright, it must be 4 times as far away. It's similar, but it's slightly different with gravitational waves. Because we're not sensitive to the intensity of gravitational waves, we're sensitive to the amplitude. It's just an inverse law. So for our gravitational waves, if they're twice as far away, we hear them, because we like to do this analogy with sound rather than sight. We hear them at half the amplitude. And if they're 4 times away, they're 4 times less loud. And the general process is that when we measure a gravitational wave chirp, right, this inspiraling that gets higher frequency and higher amplitude and then merges and stops, is that the overall amplitude is a function of the ratio of what's called this chirp mass, which is a simple function of the 2 masses of the objects, and inversely proportional to the luminosity distance from us. What we get in the phasing of this gravitational wave is that you make a very accurate measurement of the chirp mass, and so when you measure the amplitude, you can extract the luminosity distance quite accurately. Yep. Yeah. So I said it the same thing in a different way, right? In the phasing, you watch the waveform, you see the frequency evolve. The frequency evolution tells you the chirp mass, right? So this is one thing I should have put in here in text, is that this does not require a cosmic distance ladder. This is a self-calibrating system. Later on, I'm going to tell you that that's not the case, but for now, it's a self-calibrating system. You get exactly this luminosity distance is exactly the strain amplitude that you're measuring. So hopefully everyone gets the idea that we have the equivalent of standard candles, but they're standard sirens. They're also not all the same because they all have different masses, but you take that into account here, and the point is you're able to extract for any mass an estimate of the luminosity distance directly from the gravitational wave strain. Okay. Now, what I said on the previous slide was a lie on multiple levels. Here's the first level of lying, is that you don't measure this mass of your compact binary coalescence directly. What you measure is the redshifted mass. I'll play a little animation. There we go. There is a heavier mass system receding from us slower than a lower mass system receding from us faster. I think I've got this the wrong way around. I often get it the wrong way around. I think I got it the right way around. So I'll go back to the start. Oh, it won't let me. We will wait. Okay. Come on. It's still going. It's going off the page. Come on, come on, come on. I've pressed this too many times now. Or has this died? No? Here we go. There we are. I won't press it. Well, I'm going to have to press it one more time. You'll have to sit through it. The point is, the waveform that you would get in both of those cases for the same, they're the same equal mass systems. You would get the same waveform in your detector if there was a heavier mass at a lower, receding from you, slower than a higher mass, than a lower mass set of objects receding from you faster. Right? It's just like the frequencies get redshifted. And when the frequencies get redshifted, it looks like a slower mass going round. So the faster it's moving away. So there is this Mass-Redshift Degeneracy. And this means, unfortunately, that what we only measure from these waveforms is this quantity here, mz, where I had on the previous slide, I think I can go backwards one, where I had this chirp mass. You actually are measuring a chirp mass multiplied by 1 plus redshift. So you don't actually get access to either the real chirp mass or the real redshift. You just get the product of the two. Yep. Oh, sorry. Oh, yes, yes. I'm going to talk about that in a second, yeah. But although I still think that's science fiction, a little bit, right? So yeah, you're assuming this expansion of the universe is constant expansion, not an acceleration in the expansion during the period of these things that are transient and short. So I think that's everything. So if you think back to the Mass-Redshift, the redshift distance plane, we get to measure the distance, but we don't get to measure the redshift. If somebody told you the mass of the object, the rest mass of the object before you measured this, then you can extract the redshift, and that's fine, and then you can put a point on the Mass-Redshift, on the redshift distance plane and do your cosmological inference, but you don't get that from this. Oh, yeah, here we go. Talk amongst yourselves. Yeah, I think I got it right. 50% of the time I get it right. Very sorry. They can't be going that far off the screen. I don't know. Possibly. Haven't thought. Keep thinking, because I... Okay, I'm going to play a very simple game now. And I've put a lot of time in the animation, so pay attention. Well, before I get into that, actually, so what I've got down the left-hand side is a bunch of papers. It is certainly not the extensive list of people and papers that have worked on gravitational wave cosmology, but I'm going to go through some of them, and they're grouped because some of them do similar approaches. So the very first idea I want to talk about, it was the very first idea that you've already mentioned. It was Schutz in 1986 that put forward this idea, and Walter, sadly not with us today or this week, Walter Del Pozzo, who followed up on this and did it properly in 2012. And I'll just go through the basic idea. It is not really like this, but this is hopefully the basic idea. Imagine you had a gravitational wave detection, gravitational wave 1, and you look up on the sky, and you're able to do some reasonable sky localization, you go and look, and I've got 3 possible host galaxies in my window, right? Remember, from my detection, I only get a distance. I don't get a redshift. I have no idea what the redshift is. I look up here, and I've got 3 galaxies, and what I'm going to do, I'm going to assume each of the galaxies is correct, and for each galaxy, if I can get the redshift of that galaxy, and therefore I can get a Hubble constant, because the Hubble constant in local universe is simply this expression. So I can take Hubble constant is the redshift times the speed of light divided by the luminosity distance. Therefore, I get 3 estimates. I get 55, 60, and 110 as possible Hubble constant values. What I then do is I make a histogram of these possible values. And so there's bins that are size 10 here, and I've got 3 counts now. This doesn't really help me. It could be any of those 3. So I'll observe another gravitational wave. This time, I observe 4 galaxies, and I get 4 possible Hubble constants. And I add that to my histogram. Now, you should be getting the general idea that one of these galaxies in each of those is the right galaxy, and therefore there should be one in each observation that has the same Hubble constant, or at least similar to within errors. So you can already tell from just 2 observations that the real Hubble constant value is probably around 60. All right? It's the only one that's common. There has to be one Hubble constant value. But let's just double check. We have a 3rd observation, and again, there's 4 possible galaxies. One of them happens to have a 61. That looks good. And we add this to the histogram, and we do a 4th, and we keep going, and there's a 59. So overall, if I do the final thing, I've built up this histogram, and a spike has appeared or started to appear at the correct value of the Hubble constant. And that is this general statistical approach where you have confusion noise with galaxies about how you do this through multiple repeated observations of gravitational waves. Yeah, I'll talk about that again. So this is the general idea. But you're right, galaxy catalogs are not complete. We don't have information about these things beyond, I think it starts to be about 50% complete at 200 megaparsecs or so. And we just observed our binary black holes at 400 megaparsecs with some big errors on. So the expected, we don't know what galaxies are in those blobs. Also, you know, I don't know what the scale of this, how many degrees that would represent, but you'd have to have quite a small error region to have only 3 possible galaxies in there. There should be thousands of possible galaxies, depending on how big. Yeah. So, and again, I've just put a little figure of merit up here. So some of these papers go through and have estimates for how accurately they would be able to measure some of these cosmological parameters. I focused again on the Hubble constant. Walter estimates, with various caveats, various expectations of how many sources we'll detect and with what accuracy, but he's estimating around 5% error on the Hubble constant with advanced detectors. So that's getting close to the existing errors on the Hubble constant from the current best methods. I should point out as well, I always have to point out, it's going to take us 5-10 years to get to this value. They're already there. By the time we get to our value, they may have got their value far better. So we're always chasing. So we should really be aiming for far better than this, but you can only do what you've got to do with it. Exactly. They might bifurcate. They might continue along that route, and then we've still got this window to help them out. Right, so that's that method. On to a method Stephen knows very well. I've called this distribution. So forget about this having a distance and a redshift associated with your detections. Imagine you've just got loads and loads of detections. In a particular cosmology and in a particular mass distribution for your sources, again, it's easy to think of neutron stars. Imagine all neutron stars are 1.4, 1.4 mass neutron stars. Then if you measure, if you measure the SNR distribution of those detections that you get, depending on the cosmology and the recession velocity that you get, you would see these 1.4, 1.4 neutron stars, both at different SNRs, depending on the cosmology, and you'd also expect to get them at see them at different masses, because they'll be redshifted. So you can use that combination of information, and it was first put forward by Finn and Chernoff in the 90s, looking at his chirp mass distribution that you would get under different cosmologies, different Hubble constants. If you histogrammed all of the chirp masses you measured, you get this different thing. You'd also get a similar plot for the SNR distribution of these sources. And here, again, Stephen, Jonathan Gare, and Ilya Mandel followed up on this in the 2012 with 2 papers, one on advanced LIGO and one on third-generation detectors. And this is a plot I've taken from the advanced detector one, where they did a quite sophisticated approach where they also didn't say, I know the mass of all the neutron stars, but I do know the mass distribution of neutron stars, and said that they were Gaussian distributions, and you can simultaneously measure the Hubble constant, the width of the Gaussian distribution of neutron star masses, and the mean, I think that's the mean of the neutron star distribution. So you're marginalizing over all your uncertainties and still getting a very good measurement on the Hubble constant. And again here, claiming a 10% sort of error. So it's all competitive. Any questions? Also, these are 3 different parameters. It's not come out particularly well. This is the Hubble constant. This is the width of the neutron star mass distribution, which you don't know to start with. This is the mean of the neutron star mass distribution. Because it would be cheating to say, I know exactly what the mass of all neutron stars are. They've only half cheated, right, because you said it's Gaussian. But you don't have to do it Gaussian. You can generalize this. So that's another method for doing this. But I think you need, I can't remember how many you needed. Right. Okay. So you need, with all of these methods, you need multiple detections, really, all bar one method that I'll talk about in a second. Oh. No. Yeah, avoids that. You don't have to associate with any galaxies or anything like that. So let's flip over to where you do have to associate with things. Here's one method. Again, we have another author in the room, Sathya. I've labeled 3 papers here, and it's all to do with having a gravitational wave event, specifically one where you expect there to be an EM counterpart, and that is more likely to be something that contains a neutron star, most likely a neutron star binary system that you're observing. I've got this plot here. This is for one of our follow-up searches from a gamma ray burst, because we expect there's strong evidence to suggest that binary neutron stars emit gamma ray bursts, and if we're lucky to be in the direction of the beam of those gamma ray bursts, we'd have 2 mechanisms by which to see these, one through gravitational waves and one through the gamma ray burst. Gamma ray bursts get sky localization very, very accurately, so if you do make an association of these 2 things, you can use the gamma ray burst to identify exactly the host galaxy. In this particular case, there was an initial feeling that a gamma ray burst error box overlaid a close-by galaxy. This is M31 or 81. I keep forgetting the name of the galaxy. It's a very close galaxy. If that's the case, and you identify the host galaxy, then you get the redshift. You go and look at the galaxy with your telescope, and you get the redshift of that galaxy. You use the gravitational wave estimate to get the unbiased luminosity distance, and you've got one single point on your luminosity distance redshift plot. If it's close enough, you can just draw a straight line. The inverse of the gradient of that line is the Hubble constant. And the error will be from the luminosity distance error, because the redshift will be known very accurately. Typically, our luminosity distance errors are about the scale is 1 over the SNR when we know it comes from a gamma ray burst. When it comes from a gamma ray burst, it means that the system must have been face on for the burst to get to you. So if it's face on, we lose degeneracy in the inclination angle. So then it just becomes, the error roughly scales as 1 over the SNR. So an SNR 10 event would give you a 10% error in distance. You get redshift exactly, so you're getting a 10% Hubble constant measurement from one single detection. I am forgetting that. For now, it's in the next couple of slides. So that's the general idea, and Samaya and Nisanka in 2013 looked at this for a host of joint detections, and here's her plot from her paper saying as the number of joint gravitational wave EM observation goes. Here's the relative error in the Hubble constant going down as you observe more, although it's slightly optimistic that we will even get a few to start with. This is for advanced detectors. One over 3 years, maybe? Possibly. Yeah. But it's 1 plus or minus 1, right? I mean, it's not 20, yes. You can't. Well, right. Yeah. Mm. Yeah. Well, she came to Cardiff while I was there, and she gave the seminar. We did ask her about this. Yeah, I think she was very reasonable about these things. Anyway, they're claiming approximately 5%, but if you just take one event, I think it's if we're lucky to get one event, it's going to be more like the 10% side. So Holtz and Hughes in 2005 looked at this for LISA events. And if I remember correctly, so with supermassive binary black holes in LISA, what you expect is you get far higher SNR, which is giving you a better distance estimate. You're getting, because you're observing it for a lot longer during the time that LISA is rotating around its orbit, you're getting a far better sky localization and therefore more chance of observing the right galaxy. I think they had a plot where it's like a few, of order 10 galaxies in a field. But what you get on the downside is they're so far away now, you get lensing effects, weak lensing, which affects your distance estimate by plus or minus 5 or 10%, and you can't really disentangle that. But then you can make up for this by observing lots of these things and beating your error down by having lots of things. And Sathya, Bernard, and Chris van den Broek looked at this in the context of it was advanced detectors. Oh, it was Einstein telescope using GRB joint observations where you can assume we have far more many detections, and so even if it's a small fraction of that, I think you assumed 1,000 detections were going to be joint, and basically saying we're not interested in the Hubble constant, let's just fix that to what everybody else thinks it is, let's focus on the other interesting parameters, specifically the dark energy equation of state parameters. That's why I haven't got an error estimate on there. How am I doing for time? So onto some of my stuff with other people, of course. So there's two different mechanisms that I looked at, but they use the same, they use binary neutron stars, and they use this overall umbrella term of matter effects. So binary neutron stars are a little bit messier when they start interacting with each other and merging, which can be a pain, certainly a pain for modeling them numerically, but they do contain information, unlike binary black holes, which when they merge don't contain this same kind of information that I'm going to try and extract here. So what you find is, given the equation of state of a neutron star, and two neutron stars which should share the same equation of state, as they get close to each other at the final part of the merger, the final couple of cycles, they'll get distorted tidally by their own mutual gravitational fields. The amount of that distortion is a function of the equation of state, but if you say you know the equation of state, that gets imprinted on the waveform. So this exact sort of tidal, the energy is extracted from the system and put into deforming these stars, and you get that imprinted in the final few waveforms of the gravitational wave. It imprints equation of state information, but also intrinsic mass information, not redshifted mass. This is crucial because through the in-spiral part of the waveform, as I said before, you can only extract the redshifted mass, but this imprints a non-redshifted mass component into one of the PN terms. In fact, 2 or more of the PN terms at quite high PN order. What we showed in this upper plot is that depending, I'm sorry, I've gone over the axis, that's quite bad. Depending on the equation of state, we did 3 equations of state, an optimistic, pessimistic, and sort of medium equation of state. As a function of redshift, this axis goes from redshift 0.01, this is redshift 1, redshift 2, redshift 2.5, I think, over here. This is the relative error you can extract with the Fisher matrix calculation of the redshift. So in the best case, we were getting around 10% error on redshift determination just from a binary neutron star waveform. So you're getting the distance the classic way, but you can also extract this redshift information. This is for ET. This is 3rd generation. It needed to be 3rd generation. So that's one way. The other way we looked at, Sathya, myself, and Sarah Gosson, and Luciana Retzola, and another author, forgotten, Kentaro. Yes, Kentaro. We looked at the bit after the merger. So when you've got 2 neutron stars that have merged and they're living as a hypermassive neutron star before they collapse down to a black hole, they're living there for tens of milliseconds. The frequency content of the signal that you're getting from this hypermassive neutron star imprints similar kind of information. Again, you need to know the equation of state, but the frequencies you observe, they're going to imprint this rest mass information. And you can do the same trick again, and this is a sort of cartoon sketch from the paper, and it turns out you can also estimate this redshift. I can't remember how good it was. It only really worked at quite low redshift sources, even in ET, right? Because the SNR in that merger is now getting into the shot noise as the detector noise. Because these ones are ET, yeah, unfortunately. Yeah. Sorry? That's right, yeah. Yeah. Oh, yeah. But these don't become important until higher redshifts, right? So I've confused things a little bit. These are for ET. This redshift axis goes up to 2.5, but this plot is only saying we can measure the redshift. You can then go and do your cosmology however you want afterwards, which we do in this paper. This one would have done the same, except we only were able to get sensible results or meaningful results at low redshift anyway, even for ET. So Walter and Chonny Lee and myself took this and said, how well could you estimate these parameters, not just the Hubble constant, but the other parameters, using this effect and doing a full Bayesian analysis. The problem with doing full Bayesian analysis on ET simulations is that you need to do millions of the things. It's very, very hard to even do 1 or 2. So what Walter did, he managed to do, I think, of order 100, possibly 1,000 simulations, estimating how well he could measure all the cosmological parameters. And then there was an extrapolation. So we did 100 and 1,000 and extrapolated, and 10 and extrapolated from there. And the general type of number that was coming up for the Hubble constant, I can't remember the other ones, you'll have to look at in the paper, was about 0.1%. Question? Oh, sorry. No, that's right. So yeah, that's right. Yes, exactly. So Walter especially plays both sides of this game. We write cosmology papers saying we know the equation of state, and he writes papers saying I know the cosmology, I don't know the equation of state, and it's very smart. So yes, the argument goes as follows, that And I don't really buy this argument that in early days of ET, we will make a very high SNR detection of binary neutron star merger, and we will get a very accurate estimate of the equation of state using existing Planck, Hubble, and cosmological parameters to unbias us. Well, see, so I'm pedantic about this, right? If you take the fact that there's a 5 to 10% error in the Hubble constant, then you'll get a 5 to 10% error in the mass, right? And yeah, 1 plus Z. No, the error is in the Hubble constant. No, you're right. Hang on. I don't think it matters, but I'm interested in systematic biases creeping in. So what I was going to say, yeah, right. Anything we do, I don't know how this follows through to our ultimate measurement of the Hubble constant that we want to make. But if we want to make any measurement at 1% accuracy, we need everything prior to that to be better than 1%. So I agree with you. But at the level that everything prior to it, I believe you can do all of this simultaneously because I don't think that they're degenerate anyway. But I was saying that the basic argument people say is, we're going to make this really loud, high SNR measurement, we'll be able to pin down the equation of state, and then we'll be able to do all the rest of it. I believe that we won't do it quite like that. We'll do it all together. We will simultaneously estimate the equation of state and the Hubble constant as one big model with these three parameters. Yeah. So is that... Yeah, they'll separate out. Right. I don't know. Yeah. I think it's going to be somewhere in between. We're ultimately going to do it all together. Yeah. Yeah. If you want to do an order of magnitude estimate, you can do this idea of, we'll measure this first and then do this, but we're ultimately just going to do it all together. Yeah. Right. So, that's this approach. Now this is new, and I'm really not up to speed on this. So if anybody has any insights, please tell me or add them later. But there is an existing technique in EM cosmology for finding strongly lensed images of variable sources, and by measuring the time delay you see in the two images of this lensed thing, lens object, with assumptions about the gravitational potential of the lens, because you don't know it exactly, you can work back and estimate cosmological parameters based on the time delay that you measure these images, the variation in the images. Now, it's not so good for EM because it's very rare that you have very accurate timing information for images and their variability, but for gravitational waves, certainly compact binary coalescence, we can get the arrival times of these things to fractions of seconds. So and again, this is a prediction for advanced detectors at full design sensitivity that we may get one or two strongly lensed events where you see the difference in arrival time. That error is super tiny compared to the systematic uncertainties of your prediction of the lens potential, but still, they're expecting with a handful of detections, you get down to the Hubble constant of 1%. I think it's a bit optimistic, but it's certainly something we can look at for third generation. Thanks. So that's all I'll say about that because I don't have too many details. And this one I always like to put in, and this is what you were mentioning before, that if you observe a source for so long that the redshift, the acceleration, that it's moving, how do I explain it? Yeah. The universe is expanding, so it's accelerating away rather than just moving away from us. And this shows up, this will show up in a, you might notice this is shrinking and moving away from you incredibly slowly. Hopefully it won't take half an hour. This turns up as another PN coefficient in your binary waveform, which is resolvable different from the other PN coefficients, and it shows up and you can measure this expansion. It is extremely cool. Well, Disigo, it's Disigo, that's why it's sci-fi, it's a bit... Yeah. Yeah, I know. Yeah, it's Disigo, and they quote things like 16-year observations, so that was, I just had a quick scan of it, maybe that was one of their numbers, and... Right. Yeah. 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 I love this. One of the things I always try and do is, if you can't do it with one source, can you do it with an ensemble of lots of sources and build up the SNR? And it would be something I would be interested in finding out exactly why it's not going to work for Lisa, and whether or not you can put loads and loads of sources together and get a measurement. But I'll bring that up at the end. So that's disappeared off into infinity. That was all the ideas. Right, some pressing issues. Okay, yeah. Inaccurate rulers and too many galaxies. So it's already been pointed out that there is the confusion noise approach, which is the easiest one, where you get a sky map and you go and look and count the galaxies and do this histogram kind of approach. That's kind of the easiest to start with. It's probably just as easy as your approach, Stephen. But one of the problems is looking at these posterior distributions on distance and sky for the existing detections that we have from LIGO for the binary black holes, the amount of volume contained within these posteriors and totally on the sky, the number of galaxies in each of these, is of order 10 to the 4 galaxies. So my little approach would have taken a long time for it to converge on the single value, right? So this is a problem for binary black holes. There's one sort of solution for this, and for binary neutron stars. I also wanted to add, that was also mentioned, even if you do have these areas and you go and look for the galaxies, we don't know what's in those areas because the galaxy catalogs don't go that far, and it might be just too big of an ask to say, hey, really good telescope, can you go and map all of these 5,000 galaxies in this sky block? There's no real rush. It's not one of those rapid follow-up things. You can take your time, but the gains are going to be low, seeing as we'll need hundreds of these, if not thousands, to make a sensible measurement. So this is slightly problematic. Other problems, again, Ricardo has pointed this out. I think you've noticed all of the problems before I've said them, that calibration is a problem, right? Actually, absolute calibration, there's absolute calibration and there's phasing calibration, but I'm focusing on absolute calibration of the gravitational wave detectors. Up until now, everybody's been happy with of order 10% calibration, because everybody, quite rightly, has been thinking about single detections. How good does the calibration need to be for us to make a detection of gravitational wave and make a sensible estimate of the errors? If you want to combine lots of events and you want to do cosmology, you need better errors than this. I've got another plot in a second. So the general idea is it's 10%, but they are working on this to get it better. But whatever error you want on your Hubble constant, I'm just focusing on Hubble constant, you need that to have better calibration error than that in your detector. Unless, and unless this is true. So I've been talking to the detector people, lots of them. Finally, we're starting to talk on the same level. I'll go through a little bit, just an example here, right? If the error on your calibration for every detection is a random variable drawn from your error distribution of 10%. So if every day the detector resets itself and suddenly draws a random calibration uncertainty that it has, it's still 10%, but it's just a random unknown variable, then every single one of your subsequent detections will have a random 10% calibration error. But the more and more detections you get, the tighter and tighter your error your estimate can get, and you get closer and closer to the truth. And that's fine. Maybe we just need more detections to get to our desired accuracy and Hubble constant. Well, it's just going to be beating down. If it's going to go as the square root. But right now, I'll take anything. I would have a really awful error from LIGO as long as they could tell me it was different every day, right? But right now, it's looking likely that LIGO has one number and it's unknown. It's a very, yeah. The detector varies, but there are. Yeah, but it's not. Again, I've spoken to Culhane guy. He's doing the analysis, and a load of people at the detector, all about this. And it's not entirely clear the number that we're interested in is the number they're taught. It's strongly related, but when I keep asking, is there this systematic that is one of the things they all say is there is an ultimate limit to how accurately they can calibrate LIGO right now, which is the pcal, which is the error in the laser they use for the calibration of the device. Is it laser? They fire photons, right? Right. So, yeah. But that's the same laser every time they do it, and it comes from the manufacturer with a calibration on it, and it's 0.4%. And that will be most likely the same error point in there for the rest of advanced LIGO. So that would be the ultimate systematic error. But it's a very, very complicated system, and it's not clear that there are other things that come in that also have those long-term variations. Their estimate of the error does vary. That was the distinction. Does their estimate of the error vary, or does the error vary? And it's not super clear. Anyway, that's one point I wanted to make, and here's my plot of if every single one of these is off by 10%, then all you have to do is you just have to live with it, because ultimately you make more measurements, but you have to have a bigger error bar overall. You can't beat down your 10% error. And that will kill any estimate. All these papers that say we'll get down to 5%, you know, it's not quite true. It's the luxury of writing these theory papers years in advance. You don't have to worry about these things. I want us to talk about stuff, so I'm at the hour. I'm going to go quite quickly. It was already mentioned as well that you can... You have a question? Right. Oh, yeah, yeah. But there's one where every one of your weak lenses, as long as they're different places on the sky, is going to be a different error in a different direction, demagnifying or magnifying, and you'd hope to beat that down. Again, I'd rather not have those errors, but it's better than having a systematic. Yeah, yeah. 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 So this is in the spirit of flipping things round, where I, said we know the equation of state, we don't know cosmology, and vice versa. Forget about equation of state. Let's just say that we've got calibration and cosmology. We wrote a paper last year, Matt Pitkin, myself, and a student, where we just say we know cosmology, but we don't know the calibration of our detector. Let's calibrate our detector using astrophysical sources. It's a nice little cute project. So these were the results that we came up with. Again, it's a bit pie in the sky. It's similar to the GRB case, because what we did assume is that we see a handful Did we say a handful? No, we see one. We said we see one joint gamma ray burst detection with a binary neutron star merger, and we get the distance from the gravitational wave, and we get the redshift accurately from the gamma ray burst. And we find as a function of distance, our calibration error is comparable with the sort of canonical 10% that LIGO has tried to stick with up till now. So at very best, at very worst, we could validate an existing calibration, which is a nice thing to do, at the sacrifice of doing any cosmology. We're using the null stream this week for everything, so I wouldn't rule it out. I don't know how. The next stage of this was to do, I don't know if this is related, but to do inter-detector. This is for single detectors individually. So I don't know if this is related. You know, if you have a signal coming in, you expect it to have the same amplitude in both detectors, give or take the polarization, marginalizing over the polarizations and things. Yeah, so that's what we want to do. And you can do that if we ditch absolute calibration. If we say we don't want absolute, we can do relative between all the detectors. Yeah. So that was just a nice little novel thing. Here is the one current strong idea in LIGO, for those people that think about making cosmological measurements, is this thing called golden. Oh, it's already started and it goes behind the plot. That's awful. Sorry about that. Should have been classier. There's this thing known as golden events, and golden events are these terms. It's been used for various different things in LIGO, meaning all various different things, like really high SNR, which is highly correlated with small sky error, which is highly correlated with how many galaxies you expect to see in there. So one thing that Xinyu Chen and Dan Holtz have been looking at is exactly how many of our events, what fraction of our events would we expect to only contain a single galaxy in the error box. And here are some of their results for 1.4, 1.4 neutron stars, 10, 10, and 30, 30 black holes. And the three different curves are for the three different epochs, I think 01, 02, 03 of LIGO, but they don't really differ too much. This is the expected number of galaxies you expect in each error box, assuming on average 1 galaxy per 100 cubic megaparsecs. That's the average. Yeah. So you can read off here, or you can look on this table where they put all the results together. These are for different 01 and design for different detector network combinations for the different masses. This is the column that's important, and within this column are pessimistic, realistic, and optimistic event rates, because it's a function of the event rate of how many you expect. And it's not brilliant news for advanced LIGO, but in this optimistic case for HLV03, oh, actually, no, in design, oh, no, that's quite good. I didn't see that number. I thought it was 2.3. There is this possibility of a few to tens in the most optimistic case of rates, where you only get this one event with no other galaxy confusion, right? You do the very first game we played, but there's only one galaxy in each, so it's just easy. In which case, your error is going to be dominated. Unfortunately, it's not as good as the gamma ray burst because they're not going to be face-on. You don't know the orientation, and that typically makes your distance errors, rather than 10% for an SNR 10, it's more like 30% for the same SNR. So you require a few more events to put together to beat down this Hubble constant measurement that you'd make. But that's the general thinking. I don't like this. because it's too elegant and I didn't think of it. Yeah, it's the special case of only using the loudest events and throwing away every other detection that you had where there was more than a few galaxies in your field. Yeah, it's guaranteed to be worse, but by how much? And that's what Laurence has been looking at. So this is very preliminary results, and it doesn't, I wouldn't trust these at all. I made these. We have a student looking at how to do this using a sort of unbiased Bayesian approach where you don't just look at the gold and you look at all of them, right? And what you're seeing here, let me see if I can remember, each of these these are posterior distributions on the Hubble constant, and each of them are from different events. Each of those different events has a different random number of galaxies in its field, and you can see they're quite bad individually. There's one grey one here that stands up because there was one loud event. There happened to be one loud event with only one galaxy in the field. And the black is the combination of all of them doing it correctly in an unbiased way, taking into account all of the biases about galaxy cataloging, completeness, and all sorts of things. And I picked this example to try and highlight that we're right and everybody else is wrong. It doesn't always work like this, but if you took the loudest event, you will get a biased result, just slightly outside of 1 sigma error. If you put everything together, you get a nicer result. The width of those results is quite similar. So this is telling me that the power of all the other ones is not really helping you refine your precision, but it is making your estimate more accurate. And here is a plot showing the same result. This is 90%, the red contours, or sort of the 90% confidence error on the Hubble constant. And as a function of event number, as we add more and more events to this, more and more gravitational wave events, each one of which has a field with confusion noise. Yes, exactly. That's exactly right. And the blue plot is showing the SNR of the individual detections. And as you can see, when you get a sort of sudden spike, one of your high SNR events, it tends to have less galaxies in the field. It really helps kick down this error because you've just had a sudden spike. But it's all of the other ones combined that drag you back onto the unbiased approach. Yeah. It's too early days. I really hope that's the case. I really hope that this work is useful and it isn't just a waste of time because Xin Yu and Dan Holtz are really smart and just say we want to look at the golden events. So I hope it's the case, but we don't know the answer yet. So I need ideas, right? Yeah. So this is, again, I'll run through these and then I want people to throw things at me, ideas at me. Right, advanced detectors, black hole binaries. If we only get binary black hole systems, what should we do? Because all of the high accuracy methods all really rely on binary neutron star mergers for many reasons that I've talked about. Galaxy confusion may kill us with binary black holes because their error bars, their error regions on the sky are so much larger than binary neutron stars. So the sky position is a function of many things, one of which is the SNR and the frequency of the merger that you see. If you see a high frequency, get good SNR at high frequency of the merger, you've got far better sky localization. So binary neutron stars go up to 1.5 kilohertz, and they go right through the bucket, but binary black holes merge before then, so you don't get as good relative timing between the two detectors. 3 detectors. So that's one thing I should have added, which I'll add in, well, I'll say it now, right? So when I was at the PAX meeting last year, I was saying all of this, complaining about calibration and all sorts of things, and then Rana gave his talk after me and said, all of that's irrelevant. We just need to build a space-based interferometer for cheap that is just very small LISA that goes around the Earth, and it will give you a baseline that will give you sky localization and wipe all of our sky localization errors down to sub-arc second and solve cosmology. Yeah. 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 But his cell was for a cosmology session that it would just be for sky localization. Yeah. So I forgot to add this to here. We're unlikely to get a golden BBH system. I think that was true. What is that? Yes. We are unlikely to get, I'm pessimistic, right? We're unlikely to get an EM counterpart. Well, no, yeah, for binary black holes, I mean, I don't think we're going to get an EM counterpart. It'd be nice if we did. Even if we did, the sort of EM counterparts that came out up during the detection were, yeah, and the error bar was massive. They didn't give a sky localization, right? A very tight one, did they? Distance inclination. Well, you'd have to have the model where it says you only got EM emission because it was beamed as a jet out of the... yeah, for binary black holes, so... No, it doesn't... Right, that's what I'm saying. I'm saying we're very people still look, right? But... yeah, I know, yeah. Yeah. Oh yeah, we'll get degeneracy in these of 30 to 40%, just like we get for binary neutron stars without an EM counterpart. It's the same inclination angle. No, golden... if it's really high... but golden, in my case, is golden that you have high SNR and a small sky localization and therefore one galaxy. Then you know the redshift, irrespective of the orientation, you know the redshift. And your distance will be degenerate with inclination, like you're saying, just like all other mergers. But you need very loud. Yeah. Yeah. Anyhow, right. Other thing is, can we use? I'd love to use Stephen's method, where it's about the mass distribution. You don't have to assume exactly the mass distribution. You can do some fancy Gaussian process modeling for a completely unknown mass distribution, and then can you do this statistical, not confusion noise galaxies, but the distribution of SNRs and measured masses combination? Yes. Yeah, because, yeah, it is, most likely. Even if it was pinned down exactly the shape, it's very broad. But can we do anything? at all. And this final one, this keeps me up at night. I thought I was onto a roll with doing this with binary neutron stars. There's a trick to get the mass out, right? And then you can get the redshift. Surely you can do this for everything, but you can't do this for binary. You can't do the same thing for binary black holes. The tidal, there's no tidal deformability parameter to break this degeneracy. So, but it scales out, doesn't it? You won't be able to get a true mass out of the waveform. If you can, please. Yeah. Because right now, the only way of getting a redshift out is finding which galaxy it came from, and that's a function of the sky error. So unless we can make the sky errors really great by using Rana's new space-based interferometer, which I'm sure you can just put up there in a week or so for no money, then I just want somebody to work out how to get the redshift out of a binary black hole. Right? Can we write that down? Memory. Well, it doesn't matter. Any old thing will do. Sorry? Yeah. Yeah. Right, so we've got that. Yeah, let's think about that. Right, binary neutron stars specifically. Will we get any or enough binary neutron stars to do any of these measurements? Again, I'm being a pessimist. We haven't seen any binary neutron stars. In a worst case, Sathya sort of alluded to the other day that the lower limit of 0.4 detections of binary neutron stars per year for advanced LIGO detection goes down by a factor of 4 to 0.1. That's the lower limit. It's the lower limit. The upper limit is the medium realistic would go down to 10 per year. Even at 10 per year, a lot of the papers that came out, I mean, you had 100, other people had 15 in association with gamma ray bursts. So this may not be as powerful as we want to. Will we get any golden events? It looks like it's down at the 1% sort of level of events would be golden. And if you're only getting 10, none of them would be golden. Well, in this case, it's single. In this sky localization case, it's a single galaxy in the field. Should we chill out and wait for gold? As Xin Yu and Dan Holtz say, you know, we can't do cosmology with these other ones. We need to wait for the gold. Or should we combine all of the crap below and see if we can get a good measurement? How powerful will the mass, this is the same question as before, how powerful will a mass function ensemble approach be of assuming a mass function for the, or some form of the mass function for the binary neutron star? Sorry, this is a binary neutron star thing, so that's a question directly for you. How powerful will it be when we don't have possibly enough binary neutron stars? Here's a sort of technical, boring question of if these multiple groups doing multiple measurements of, say, the Hubble constant, because that's all we can do, with the same data but different methods, I don't think we can probably multiply those posteriors together. I think they'll all probably be correlated in some way, which would be another thing we should be careful about in enhancing our estimate of our results. But I'm jumping the gun now. We haven't measured anything yet, so... Well, they're all using the same... Say in Stephen's approach, a bit of noise kicking a detection in the direction of looking like a higher mass system would do the same, would have the same effect in the other approaches, and just so it would be a combination of correlated errors, so you wouldn't be able to directly multiply the posteriors without a covariance. That will be my initial guess. I don't know whether it's an important thing. Certainly not before we've measured anything. Yeah. That won't stop people doing their worst method, of course, but... Probably. If you fix the cosmology. Right. That would be another, if you wanted to do, attempt the full cosmology, everything together, unknown mass function, you would have to have a redshift-dependent mass function as well to do this properly. So it adds, makes the cosmology more difficult. Yeah. 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 But this is yeah. But this is going down that route, which is gravitational wave cosmology not good enough. Let's use everybody else's and do other science really well, which is good. Which is good. I'm pro that. GRB counterparts, I've measured those before. How likely are we to get them? The general idea is we'll get 1 plus or minus 1 or so for advanced LIGO per year. Is it per year or per 3 years? It's of that order anyway. And it's a strong function of the beaming angle. Okay. If we get 1 per year, but that's also a function. That's a function directly of how many we detect in the first place, which has got 1 or 2 or an order of magnitude either way error. Third generation detectors. If we're many, can we? Yeah. So this is what I was arguing with Sathya about. I would like to, but adding an extra thing as well, the calibration. Depending on the calibration model, can we measure the neutron star equation of state, calibrate the instrument, and do cosmography or cosmology simultaneously? Are they all orthogonal enough in the data that you can make estimates of all of these? And hell, why not throw in a mass distribution for black holes and a redshift metallicity thing and do the full deal? It's the event rate of what? I don't know if the numbers have changed, but it was 10 to the 4 to 10 to the 7 per year last time I looked. When Sathya wrote his papers about this. Sorry? Yeah. And seeing as we haven't detected any binary neutron stars yet, haven't ruled the lower edge yet, so 10 for advanced as the realistic rate. Astrophysical stochastic background, astrophysical stochastic background of all the binary black holes. People in LIGO think we might just be able to detect maybe in advanced LIGO this background. Will that contain any, they have to assume a Hubble constant in there, but is it high enough SNR that they'd be able to relax that and estimate a Hubble constant? I doubt it. If they're on the verge of detecting it in advanced detectors, what about ET? Will this be a high SNR background in ET? Will we be able to estimate parameters, cosmological parameters out of that? That would be interesting, if possible. I've written this so many times now, this about the mass function stuff, right? So, and lensing. I think Sathya said, no, lensing, not for third generation. So we don't have to worry about lensing. Or a lensing approach, that was it. A lensing approach like the, it was the time delay from strong lensing. They've only written the paper about advanced. I think they're a bit optimistic, but maybe if we pushed that, we used that for third generation, it would do all of this for us. I don't know much about space. How big a problem will lensing be? I'm sure I should have filled in lots of other things for this. We'll come back to that. General questions. So the papers generally that do this for ET just say, I don't care about the Hubble constant. I'm just going to fix it to Planck value, and I will estimate the other parameters. Whenever I talk to people, I am accused of being obsessed with the Hubble constant. I think I've said it about 1,000 times today. I only like it because it's just it's a nice simple problem that we can make a measurement that's independent of other people's measurements. How impactful it will be if we end up making a 10-20% error measurement on it, no one will care. I'll care, as long as we did it right. But should we ditch it? Should we just say we're going to assume somebody else's? It then means that all of our further cosmological measurements, unless we're very, very careful, which might be impossible, would be biased by any existing bias in other people's measurements. It'd be a validation. It'd be completely independent if we don't use any of their numbers. Yeah. But it's got varying degrees of power. If it's plus or minus 10% and it overlaps both supernova and CMB measurements, then well done. You know, you're not wrong. But if we are more in line at 1 or 2% with one of those, that's exciting. Yeah. If we agree with if we agree with the supernova, and if you argue that they are fundamentally different measurements they're really making, then we should agree with the supernova. We're doing the same local measurements, and then that points to new physics. It's more evidence towards a reason for the tension. But if we go the other way, it just says the cosmic distance ladder is poorly calibrated. Yeah. So there is stuff to get out of it. It just depends on the effort to get down to the 1 or 2%. And by the time we've got to there, have they moved on? Have they resolved already? I'm pro doing this because I think we shouldn't not do things. We should always do them. And yeah, my final point, again, to reiterate, can please somebody make binary black hole systems more useful for cosmology? And I think that's everything.